Hello, dear students. In the previous class, we were discussing about the valence bond theory and the modified valence bond theory, that is hybridization. Today, we will look into the structural aspects of certain molecules. I have taken three molecules over here: nitrogen, oxygen, and fluorine. And I have drawn the Orbital structure of nitrogen, oxygen, and fluorine. And before getting into the topic, there are two terms. One is paramagnetic, the other one is diamagnetic. What is paramagnetic, if you ask? Paramagnetic substances are the substances which will get attracted by a magnet. Diamagnetic substances are the substances which will not get attracted by magnetic substance. So, paramagnetic substances shows the magnetism, diamagnetic substances will not be identified by a magnet. And if you ask me, what makes a substance to be paramagnetic? The answer to the question is, if there is unpaired electron in a substance, that will be paramagnetic. If there is no unpaired electron, that is diamagnetic. So, the presence of unpaired electron will make a substance to be paramagnetic. The absence of unpaired electron will make the substance to be diamagnetic. So, here we have taken three molecules. And if you look at this molecule, nitrogen, you could see there is 3 bond pair and 2 lone pair. If you take oxygen, 2 bond pair and 2 lone pair. If you take fluorine, 1 bond pair and 3 plus 3, 6 lone pair. And you cannot see any unpaired electron. When there is no unpaired electron, you can't expect the substance to be paramagnetic. So, if you take, for example, NO, nitrogen monoxide. Nitrogen monoxide is paramagnetic. Even by Orbital structure, if you draw in whichever be the way you draw, you can't end up drawing the Orbital structure of nitrogen monoxide without having an unpaired electron. So, there is unpaired electron and it is paramagnetic. There is no complexity. Whereas, they have done an experiment. Of course, the observations from the experiments that need to explain, that's why science grows by explaining the observations, giving explanation for the observations what we have made. It's the science means it's the explanations made for the observations what we have made in various experiments. So they have done an experiment. They made liquid nitrogen. How do we make liquid nitrogen? We can cool a gas. If you reduce the temperature of a gaseous substance, it will get liquefied, it will get condensed. So, we made liquid nitrogen, we made liquid oxygen, we made liquid fluorine. And how do we understand whether it will get attracted to the magnet? What we have to do, we have to pour it in between the opposite poles of a powerful magnet. And we have taken these 3 liquid and poured in between powerful magnet, the poles of the powerful magnet. And nitrogen didn't get attracted to any of the poles, that means it is diamagnetic. Fluorine didn't get attracted to any of the poles, that means it is diamagnetic. Whereas this oxygen molecule, even though it is having no unpaired electron, it has got attracted to the one of the poles of the magnet. What does it mean? So, experimentally, or we can say empirically, the oxygen molecule is paramagnetic. So, VBT says that, Orbital structure says that there is no unpaired electron. Valence bond theory says that there is no unpaired electron. But it shows paramagnetism. Then there is something to be modified so that we can explain the paramagnetism of oxygen. That's why we have brought into molecular orbital theory. Molecular orbital theory. Molecular orbital theory have a set of postulates. If we compare, like if we take valence bond theory or Louis dot structure, we focus on the electrons which is involved in bonding. When you talk about the molecule, what is the focus if you ask? It is the orbital which is involved in overlapping. We don't bother about the other orbitals. Point number one. And the second point is, if you take H2O, or if you take like H2O, if you take H2O, that is sp3 hybridization. This is how. So 2 long pairs plus 1 long pairs. So this 4 sp3 hybrid orbitals belongs to oxygen, and these 2 belongs to hydrogen. They still retain their identity. The atomic orbitals retain their identity. But MOT is having a different concept. MOT says that each and every electron or each and every orbital inside the atom is involved in bonding when it is forming a molecule. That's what the idea behind molecular orbital theory. So let us see what are the postulates given by molecular orbital theory. So very first postulate it says that just like atomic orbitals are for atoms, molecular orbitals are for molecules. Molecular orbitals are for molecules. Molecular orbitals are for molecules means for atoms you cannot see molecular orbitals. So what is atomic? Just like atomic orbitals are for atoms, molecular orbitals are for molecules. So what is an atomic orbital? So atomic orbital is a wave function which represents a 3-dimensional region where the probability of finding electron is high within an atom. Whereas molecular orbital is a wave function which represents a 3-dimensional region where the probability of finding electron is high within a molecule. Within a molecule. So just like atomic orbitals are for atoms, molecular orbitals are for molecule, and what they wanted to say is that just like atomic orbital is having a particular size, a particular shape, particular energy level, molecular orbitals are also having particular size, particular shape and particular energy level. So they are characterized by size, shape and energy levels. And the second point is how these molecular orbitals are formed. So we have already told it's like atomic orbitals are for atoms, molecular orbitals are for molecules. And the second point is how these molecular orbitals are formed. A molecular orbital is formed by linear combination of atomic orbitals. Linear combination of atomic orbitals. Linear combination of atomic orbitals. So actually the atomic orbitals means it's nothing but a wave. A wave. And so we have learned the Broglie events and all those things. It's a long story. If you take two waves, it could be in phase or out of phase. Suppose if you take this wave. So it could be like this. You are taking another wave. So this wave is out of phase. If you combine these two, what will happen is there will be nothing. Nil. Because this wave get cancelled by this wave. They are opposite in phase. If you take another wave, if you take this one, like this, you could see that these two are in phase. So what happens? Wave
with high amplitude.
A wave with more amplitude. That's all. And the atomic orbital concept, they say a wave function psi a for a wave or an atomic orbital, for a wave or an atomic orbital plus psi b. So it is just to make you understand. Just say that according to your example, you can say linear combination of atomic orbitals. There is one more possibility, psi b. It gives, this is how it is given, psi a b and psi star b. So there are, just to make you understand, it's a wave, atomic orbital is a wave, so they can get added to form a big wave. This is a extreme end, completely added and completely subtracted.
But when we talk about the molecular orbital formation, no two atomic orbitals come completely out of phase or completely in phase.
It comes somewhere between. So I just wanted to make you understand that atomic orbitals go for linear combination in order to form molecular orbital. This wave function represents molecular orbitals. So
Molecular
orbitals are formed by linear combination of atomic orbitals, and you have to take one more point, that is number of molecular orbital formed will be exactly equal to the number of atomic orbitals combined. Number of atomic orbitals combined. So, just like atomic orbitals are for atoms, molecular orbitals are for molecules, and molecular orbitals are also having definite size, shape, and energy limits. And molecular orbitals are formed by linear combination of atomic orbitals. There are two types of molecular orbital. One is, I have told, subtracting wave. Could be represented like we represent the molecular orbital, like we represent by box type. Suppose if you take hydrogen, atomic orbital of hydrogen is 1s, will represent by a box. So, two atoms, this will be HA, this will be HB, atomic orbital 1s, for H hydrogen atom B, atomic orbital 1s for hydrogen atom A. So you represent, when you draw the molecular orbital diagram, you take atomic orbital A one side and atomic orbital B on the other side. And if you wanted to represent the molecular orbital, you draw it on the middle side. So this is atomic orbitals, here also atomic orbital, this is molecular orbital. So if you wanted to represent the molecular orbital, you represent it at the middle. So I have already shown over here that it could be subtractive mode and it could be addition mode. Linear combination, there could be two types. So if it is, I have written one with the star and one without star. If it is without star, we call it as bonding molecular orbital. And bonding molecular orbital will have lesser energy than the standing atomic orbital. So I will represent it here like this. This is by addition mode, and this is by subtraction mode. So this is when 1s and 1s join together, two molecular, same number of molecular orbitals, they are named sigma 1s and sigma star 1s. So this is how it is represented, like this. So they are, so this end atomic orbital, this is the way of representing the molecular orbital. Here atomic orbital of the second atom, first atom, molecular orbital will build up at the center. So if 1s and 1s join together, they can go for linear combination, subtractive mode and addition mode. When it is subtractive mode, they will have more energy. When it is addition mode, they will have less energy. And the molecular orbital which lesser energy than the starting atomic orbital is what we call bonding molecular orbital. And the molecular orbital which has more energy than the starting atomic orbital is what we call ABMO. It's called anti-bonding molecular orbital. We are understanding the molecular orbital is formed by linear combination of atomic orbitals. There are two types of molecular orbital. One is bonding molecular orbital. The other one is anti-bonding molecular orbital. And the bonding, you have to say just like this. A bonding molecular orbital is molecular orbital which has lesser energy than the starting atomic orbital. If you have any doubt, we can go like this. As we move up energy, increase it. So this will have lesser energy and this will have more energy. The molecular orbital which has more energy than the starting atomic orbital is called anti-bonding molecular orbital. And you might be asking why this anti-bonding molecular orbital is having more energy. So this is how the diagram will work. If you take a orbital, this is how the S orbital normal S orbital, atomic orbital. When they are going for linear combination, they can have two mode of linear combination. One is subtracted mode, the other one is addition mode. When it is side A minus side B, what happens? It is subtraction, like it comes like this. When it is addition, it comes like this. So this is one atom, one nucleus, atom, one nucleus, atom, two nucleus. This is anti-bonding molecular orbital. Of course, this is bonding molecular orbital. And please understand this is formed by side A plus side B. Addition bond. And here, if you ask like what makes two atoms of hydrogen molecules together, it is just like in a tug of war. You take hydrogen, two hydrogen atoms. These two, this is a nucleus and this is a nucleus. Two electrons are over here. This nucleus will be pulling this pair of electron, and this nucleus also will be pulling this pair of electron. That's why these two nucleus are together. Just like a tug of war. Means in tug of war there is a rope. Both the team will be holding on the same rope. They are together. So the same way, this nucleus will be holding on this pair of electron, and this nucleus will be holding on this pair of electron. Of course, the distance matters. When there is a repulsion between these two, and there is attraction between these two. Whenever the attraction is greater than the repulsion, a bond is formed. This is how molecularly valence bond theory picture the bonding. So here, what is lacking? Here, there is no possibility of finding electron in between or at the center, in between the nucleus. Whereas here, if you see, you could see the probability of finding electron is high in between the nucleus. So this molecular orbital does everything for the sake of bonding, whereas this molecular orbital, which is anti-bonding molecular orbital, does nothing for the sake of bonding. So this anti-bonding molecular orbital and this bonding molecular orbital, when it is not doing anything for the sake of bonding or for the sake of attraction, we have more energy, because we have lesser energy. So the point number 2, an atomic molecular orbital is formed by linear combination of atomic orbitals, and it could be subtractive. You don't have to say subtractive mode or additional mode. You just say that the number of molecular orbitals formed will be exactly equal to the number of atomic orbitals combined. And one more point you have to say is that would be the third point. Third point is giving explanation for what is bonding molecular orbital and what is anti-bonding molecular orbital. So a bonding molecular orbital is the molecular orbital which has lesser energy than the starting molecular orbital, and anti-bonding molecular orbital is having more energy than starting molecular orbital. And the fourth point is Just like atomic orbitals are filled with electrons according to Hofbauer principle, according to Pauli's exclusion principle, and according to Hund's rule of maximum multiplicity. Molecular orbitals are also filled according to Hofbauer principle, Pauli's exclusion principle, and Hund's rule of maximum multiplicity. So, molecular MO are filled with electrons. They mix, like you can write according to Hofbauer, Pauli, and Ansel. To be told in another way, that is, the molecular orbital with lowest energy will be filled with electrons first, and there will be only 2 electrons in a molecular orbital, and pairing of electron happens until each orbital is singly occupied. That is the third point.